Hello and welcome back to this video on empirical banking and finance. In this video I'll be talking about causation versus correlation. So in essence, establishing causality in an empirical analysis. We've already talked about this in the last video on research questions, and I stressed the fact that you need to establish causality and you need to think about causality in your research question already, and when you come up with your research question. And we want to go back to this question of causation versus correlation. Now imagine that you've come up with a clever research question, that you have a relevant research topic, and now you want to test your hypothesis that your explanatory variable x causes your outcome variable y. And almost all statistical tools that you have, especially linear regression analysis, all those methods you have at your disposal, they test whether those two variables are correlated, but they do not show you per se whether you have causation running from x to y. So these methods test for correlation, but they do not test for causation. And correlation is not equal to causation. And I'll give you some examples and some cases where you will find correlation, but you cannot speak of a causal relation between x and y. So let's look at this plot here, and you can see all the different reasons why the red and the blue variables or dots here might be correlated. First of all, it could simply be chance. You will have some correlation that is simply random and that is just noise in the background. It could be that blue drives red, which in this case is the causal relation we are actually interested in. So let's assume, what do I have here? Let's assume this is our x and this is our y here. Then we get causation in the sense that we do have, where's my cursor here, that we have variable x driving variable y, but it could also be the other way around. It could be that we have reverse causality, meaning here, reverse causality, that we do find correlation between red and blue, but the problem is that the causality runs from red to blue and not the other way around. Fourth case is a confounding effect, could be also by time. Confounding effect in this sense here is an omitted variable bias. We have a variable z that drives x and y. So this variable here has correlation with x and y, and this correlation between the omitted variable and x and y, this omitted variable, this spurious correlation, that's what we call it, the spurious correlation drives the correlation between x and y. So in a sense it's a false friend, it's a false correlation between x and y. That is actually due to the correlation between z and x, so actually this one here, and y and z. And last but not least, it could simply be a selection bias, that we do not look at the whole population we are actually wanting to look at, but it is a selection bias that we have selected those observations such that we get the correlation that we want to see. So these are all those different possibilities. It could be by chance, the correlation is simply coincidental. It could be reverse causation, the dependent variable has an effect on the regressor, the explanatory variable. It could be confounding effect, or it could be self-selection, that is the outcome or the variable of interest we are looking at causes a sample selection bias, that is a non-random sample of the population, and this causes some members to be less or more likely to be included in the sample, and this selection bias causes this correlation that we detect. So the direction of causality could also be this here, case 1. This is what we're looking for. It could be reverse causality, or it could be that x drives y and y drives x. This is what we usually refer to as endogeneity, meaning that we have an exogenous effect of x on y, but the effect is not exogenous, but the effect is endogenous in the sense that both variables could influence each other. So case 1 is perfect. If you can plausibly establish causality running from X to Y, you're done. The second case is endogeneity. You're picking up effects and an effect of X on Y. And we want to do this and we want to show this. Problem is that this effect of X on Y is somewhat distorted by the endogenous effect of Y on X. And it could simply be that endogeneity and reverse causality is predominant here, and we are picking up correlation, but it's completely the wrong idea. It's simply Y driving X. Fourth case is omitted variable bias. Now I'll give you a pretty good example for an omitted variable bias in just a couple of slides. And in this case we have a variable Z, and omitted variable already points at the problem here in the context of a regression analysis. Now in a regression analysis you would look at a regression just like this, A plus B times X. And obviously you have epsilon, your error term here. The problem here is that if you omit, if you forget Z, then the coefficient B here, this one, this will be biased by the fact that you have forgotten Z and you've forgotten to include Z. So this is the omitted variable bias. B, the coefficient on X could be significant in your regression analysis. However, it's distorted by not including Z. So what you need to do is you need to include Z, and Z here is not really interesting. It's not of any importance economically. We don't care about Z, but Z is usually then referred to as a so-called control variable. You need to control for a confounding effect of Z, otherwise you will have an omitted variable bias. So the Z in this context here is an omitted variable bias. Okay, where's my cursor here? And the fourth case, again, this is the omitted variable bias. The correlation you're picking up in the original regression analysis here, when you omit Z, you will find correlation, but this is a false correlation. It's not between X and Y, it's between Z and X and Z and Y. This is what we call spurious correlation. And so an omitted variable can lead to spurious correlation. This means that although you have no causal relation between X and Y or Y and X, you still find correlation that is due to the confounding effects of one or more omitted variables. And the fifth case is if you omit a variable that is not correlated with any other regressor. This only affects the fit of the estimation. So you do have a trade-off. You can add variables to a regression model, and you have this trade-off between a better fit of the estimation and the plausibility of the model. That is, how well does it fit other data. Hence, you don't add unimportant variables to your model. And keep in mind that if you add variables to a regression analysis, your unadjusted R-squared will mechanically increase, and you need to look for the adjusted R-squared that accounts for the number of variables you're using. Let's take a pretty good example for spurious correlation. The hypothesis is that storks deliver babies. Myth that you might have heard as a child. And the research question now would be to test this hypothesis. Do counties or regions with more storks have higher birth or fertility rates? In a regression analysis, you would use XIT as the number of storks in county I in period T, and you would use YIT, the birth rate in county I in period T, and would then estimate a regression of Y on X. And the usual result here is actually that you do find a significant effect of X on Y, and ergo you would say that storks deliver babies because you find a significant result in your regression analysis. Now, this can be true, right? And what is the problem with this analysis? Now, if you revisit the different possible directions of causality, you would first say, could the number of babies influence the number of storks? So if you have more babies, you have more storks. Not directly, but if you say more children, higher population. It could mean more housing, less nature, fewer habitats for storks. But then you would find the opposite sign. So it could be to some extent that this question is endogenous, but then you would find a negative sign, a negative coefficient. But actually here, what you will always find, almost always find, is a positive coefficient, a positive effect of X on Y. More babies, more storks. So this is not the case here, but it's a confounding influence. But what is it? The answer is it's industrialization. So if you have an industrialized country or more industrialized region, industrialization causes natural habitats to be lost. So you have less storks, and families on average will have fewer babies. So it's not more storks, more babies, but it's rather industrialization causes less babies and causes less storks, and it's a classic example of spurious correlation of an omitted variable bias. Now, what can you do to plausibly establish causation? First, you need sound economic reasoning. It's always the best thing to think about your research question, just like in this example of storks. Does it really make sense that you will find a causal relation between X and Y? In the example of storks delivering babies, any normal person would immediately say this is a myth, this cannot be true. And even if you find correlation, there needs to be something wrong with this result. So you need sound economic reasoning and a theory that guides your empirical research. Second of all, you need to use sophisticated statistical tests that can help establish causality. And the most frequently used methods are difference in difference, diff in diff, instrument variable regressions, IVs, and RDDs, regression discontinuity design analyses, regression discontinuity. We'll talk about these later in later sections of this class, and you need to keep this in mind when planning your research design. Now let's go to a second problem that can plague empirical analyses. Imagine you want to test the causal effect of a medical treatment at a hospital on persons' individual health. Something that is very, very relevant right now in the COVID-19 pandemic, because no one really knows which treatments work. And to show that a particular treatment on COVID-19 works, you need to show that this medicine, this treatment, is causally treating this illness and has a causal effect on COVID-19. So to test this hypothesis that going to the hospital improves health, you could use survey data from interviews of persons admitted to a set of hospitals. That is, you ask them how healthy they are before and after their hospital stay, and people who have not gone to the hospital. Now, what kind of empirical results do you expect to find? Case 1, hospitals improve health, plausible. If you're sick, you go to a hospital, you get treated, and you recover. So yes, X causes Y. Case scenario 2 and 3, endogeneity and reverse causality. It's also possible. Why? Well, hospitals are full with illnesses, germs, multi-resistant bacteria, and you might catch a more serious illness just by going to the hospital with a non-fatal illness. So it could be reverse causality. Case 4 is also very important. You have a variable Z, an omitted variable, that influences both the probability of a visit to the hospital and your health at the end of the observation period. And in fact, this is the most serious source of error for our investigation. It's omitted variable bias. It's pre-existing conditions. If you go to a hospital, you're probably sick. If you don't go to a hospital, you're not sick. So your pre-existing conditions and your overall health status is pretty much important. So what is wrong with this sort of analysis? The problem is that we have non-random assignment to our treatment group. Now, ideally, we would look at random persons. Some of them get treated, some of them don't. And by looking at the difference between those two groups, you can assess the marginal effect of treatment. The problem is only sick people go to the hospital, and only sick and healthy people might stay at home. So asking people who go to a hospital how healthy they are and comparing their responses to people who are healthy, that's an unfair test. So this non-random assignment to the treatment group, this causes a so-called selection bias. That is, the observations you use did not enter your sample randomly, and in other words, the composition of your sample does not mimic the overall population on which you want to make a statement. You want to make a statement on the treatment effect of any person going to a hospital, but actually the people who go to a hospital are always sick, so you have a selection bias. So doing another example, doing a questionnaire survey in front of the university, this will also allow causal statements, but only on the subsample of students, because in front of the university you don't get a cross-section of the overall population, you only get students, and you can only ask students. So students will be overrepresented in your answers, and you cannot make a statement on the overall population. So in our example, you want to make a statement on the effect of hospitalization on a random person, but the probability to receive a treatment is not independent of the person's health status to begin with. So the treatment, persons getting the treatment, and the control group, those that do not, they differ significantly. And treated persons are already sick, and the persons in the control group are already healthy, so they do not need to go to the hospital. So what can you do about selection bias? First, is selection bias really a problem? The general idea is that you might have a selection bias present, but economically it should work in our favor. For example, if you want to show that X increases Y, and the selection bias, you can establish and argue that the selection bias should actually increase Y even further, the selection bias should work in the same direction as the effect you want to study. So you could argue, I'm showing a positive relation between X and Y. There might be a selection bias, but the selection bias might even increase this effect even further. So there's no problem. We can show positive effect, and the selection bias might even increase this further. In some settings, one might be able to argue in this fashion. Actually, could also be the other way around the argument, that you argue that the selection bias might decrease the effect, but the effect you are showing is actually positive and still positively statistically significant. So it might be that the selection bias decreases the result you're finding, but it's okay, it's still statistically significant. So you need economic reasoning. You can argue that selection bias is not a problem. In some settings, you might be able to argue in this fashion. And for this, it is interesting to have a more formal look at the selection bias. So we will think of hospital treatment as a binary random variable. So DI is the treatment of person I. And if D is 0, you get no treatment. And if it's 1, you get a treatment. We are interested in yi. This is the outcome variable for a random person. But what we can only observe is y1i and y0i. So we can only observe what has happened if a person has received the treatment or not. So the potential outcomes, they are hypothetical depending on the question whether the person went to the hospital or not. That's what we can observe. So to measure the pure and causal effect of a treatment, we would need to measure the health of a person after the treatment and without treatment. So we need to measure Y1 and Y0. However, we can only observe one of them. So we only observe Y1 or Y0. And the observed health status, yi, of any person in our sample can be written as follows. And now let's make it a little bit more intuitive. Let's argue that y is blood pressure. And let's assume that 120 over 80 is the normal blood pressure, and we will be concentrating on the first one. So let's assume that's the target blood pressure of 120. What would this mean? It would mean that we can observe, for example, y, and this is we observe Y1 if you have received a blood pressure medicine, or Y0 if you haven't received a blood pressure medicine. And this is given by what? Let's assume our blood pressure is 150 if we don't get the treatment. It is 120 if we receive the treatment. We have to subtract the 150 without the treatment times D, I, whether we receive the treatment or not. And as you can see, we are actually interested in this difference here, in the 120 minus 150. Because we want to argue, well, treating a person with a blood pressure decreasing medicine decreases blood pressure by maybe 30 basis points. So this is what we are looking at. This is what we are looking at, 30 points decrease. This is the marginal treatment effect. And as you can see, what we can observe is actually included here. What would have happened without treatment and what happened with treatment. So this is our problem here. Where's my cursor? Here. Okay. So the last equation simply means that the health status, the outcome of person I, is his health status if not treated, plus the marginal effect of the treatment. The problem now is, for one person, we cannot observe the counterfactual. We can only observe what happens if he is treated or what happens if he is not treated. We cannot observe what would have happened if he had not been treated. So not both outcomes are observable at the same time. It's either Y0 or Y1. And as a result, we cannot make statements on individual causal effects, but we can observe average effects, and that's what we are trying to do here. So a naive way to tackle this is to compare the averages of the treatment group and the control group, and persons that have been treated and persons that have not been treated. And unfortunately, such a comparison of averages does not give us an unbiased picture of the causal effect. Why? Now what we can observe is on the left-hand side. We can observe the health outcome of those who have been treated and the health outcome of those that have not been treated. And as you can see, we're taking the expected value, so it's in expectation the average. However, this is can be written on the right-hand side as two parts. We can observe the average treatment effect on the treated. So we are taking the group that is going to be treated and we are observing what would have happened with these if they had not been treated and what happens if the persons in the treatment group have been treated. So this is usually, actually here, this is usually the counterfactual. You cannot observe this unless you're looking at these persons before and after the treatment. And this here is the selection bias. You're taking the average. What would have happened with no treatment for those who have been treated, and what has happened with those, the health status of those without treatment in the control group, if they had not received a treatment. So you can see here D1 and D2, D1 and D0. These are actually the control and the treatment groups. So this is the treatment group, this is the treatment group, and this is the treatment group, and this here is the control group. And the difference before, more or less, between the control and the treatment group, before treatment, this is the selection bias. Now, let's make a small example. Let's assume we have a group of persons and we are looking at blood pressure again. What would the selection bias be in this case? The selection bias would be what? Maybe I can use this, yes. Let's assume this is our treatment group and this is our control group. Let's say this is C and this is the treatment group. Now, obviously, we want the control group to mimic the treatment group. But if the average blood pressure in the control group is 150, or let's say 120. So these are the control groups, are the healthy persons, and the treatment group, I have to make this a little bit smaller, sorry, and the treatment group, those are the persons who already have high blood pressure with 150. You can easily see that what is the average health before treatment of those in the treatment group, that's 150, minus the average health status before treatment in the control group, that's 120. So the selection bias is the 30-point difference between the blood pressure average here in the treatment and the control group. If you don't take this into account, you're not comparing apples to apples, but you're comparing healthy to sick persons, and this is a problem here. So this is the selection bias, and you're interested in the average treatment effect on the treated. If you have those with already 150 blood pressure before and after. Before the treatment here and after the treatment, and this is confounded by the selection bias, and this here, this on the left hand side, this is the only thing you can observe. The average health. You don't know whether it's the selection bias or the average treatment effect you're looking at. Okay, so this is the problem here. The second term, again, after treatment in the treatment group, before treatment in the treatment group, this is the average difference in health with and without treatment, and this is the counterfactual, if in fact the person was treated. Now in observational data, this effect is biased by the second term. This is the selection bias, the ex-ante difference in the before treatment status in the control and the treatment group. So the difference in average health before treatment of those persons in the treatment and the control group. And you need to take this into account. Now coming back to our initial problem, how can we deal with this? As pointed out earlier, random assignment should eliminate the selection bias. If we use random assignment, well, the persons here and here, they should be randomly selected into two groups, and we would hope that average blood pressure is 130 or maybe 135 in both groups, and then selection bias should not be a problem. Now consider the selection bias here. In the hospital example, if random assignment is not possible, the selection bias will probably be negative, as the initial health of those hospitalized will be lower than that of the control group. So the expected treatment effect and so the selection bias have opposite signs, with the selection bias potentially driving down the treatment effect. So if you still find a potentially significant positive treatment effect, and you know the selection bias is negative, you would argue that even with a selection bias, you still find a statistically significant positive effect. So the true average treatment effect should actually be higher. So you're in the clear. What can you do also about selection bias? First of all, random assignment. In social sciences, this is hardly possible. If you think about the COVID-19 pandemic right now, even economists are calling for random testing. They want random tests in random subsamples of the population to assess the question, how many people have been infected, how many people are immune, and if you only look at the infected numbers, you cannot assess this, you have a selection bias. So think about the numbers from Johns Hopkins and Robert Koch Institute, etc., and think about the selection bias in these numbers and why you need random testing with random assignment to tackle the selection bias here. Very good example. Now, what you can do in medicine, in pharmacology, you can do clinical trials. Then you construct random assignment as a prerequisite, and the selection bias should not be a problem. However, in social sciences, you hardly get the opportunity to do a clinical trial, only in experimental economics, so in behavioral economics. So what we need in economics is what we call quasi-experiments, natural settings in which by accident you have a randomly assigned control and treatment group, but this is only by chance. What can you also do? You can use statistics. This is Hackman two-stage correction. Hackman correction in the general idea is to incorporate information on the probability of entering the treatment group into your statistical analysis and correcting the selection for the selection bias. We'll learn more about this later on, but this is my idea of explaining to you the pitfalls of simply taking correlation and simply looking at correlation. You need to think about these confounding effects, reverse causality, endogeneity, and especially selection bias, and you need to control for this and correct for this in order to plausibly establish correlation. So this is section 1.5. In the next video we'll be talking about the research design.